Welcome. In this session, we'll learn one of the most important signal processing operations, that is how to convert a continuous time signal to a discrete time signal. In the first part, we will learn how to convert a continuous time signal to a discrete time signal, and this is referred as sampling operation in signal processing. So converting a continuous time signal to the discrete time signal is the sampling operation. Now, once we convert this signal to a discrete time signal and the required operation is performed on the signal, like the first question that we can ask is why do you want to convert a continuous time signal to a discrete time signal? And the answer is because discrete time signal processing offers several advantages over continuous time signal processing that we have already discussed in the first lecture. For example, it's cheaper, the noise tolerance is better. So once we convert the continuous time signal to the discrete time signal and perform the operation, for example, if you want to perform the operations like filtering, and if you wanted to suppose, or if you wanted to remove the distortion present in the signal, or simply if you wanted to store the signal on a computer. Once these operations are performed on the signal, how do we convert back this discrete time signal to the continuous time signal? Means how do we reconstruct or recover the continuous time signal from this discrete time signal? This is referred as reconstruction operation. So in the first part, we'll learn how to convert a continuous time signal to a discrete time signal. And in the second part, we learn how to reconstruct or recover the continuous time signal from the discrete time signal. And in the second part, we learn one important condition: at what rate should the continuous time signal be sampled so that we can recover the continuous time signal back from the discrete time signal. And in this we shall learn in the second part of this lecture. So our goal in this few lectures is to first convert a continuous time signal to a discrete time signal, then reconstruct or recover the continuous time signal from the discrete time signal. And in the second part, we will learn one important condition, that's at what rate we should convert this continuous time signal to the discrete time signal. So we shall learn that in the second part of this session. All right. So before I proceed with this sampling operation, means how to convert a continuous time signal to a discrete time signal, first let me say a few notations that will be followed in this session. So I will mention few notations here that we are going to use. All right. If I say domain, and I'm going to use it quite often, and domain can mean either time domain or frequency domain. So when I say domain, it either means time domain or frequency domain of the signal. So when I say time domain, I am simply saying x of t, or in discrete time, I can say x of n. Same way, if I say frequency domain representation of the signal, I will say x of omega. X of omega is the frequency domain representation of the same signal I'm talking about. So whether I say x of t or x of omega, I mean one and the same thing. But where x of t is the time domain representation, frequency domain representation is given by x of omega. And what's the relationship between x of t or x of n with x of omega? We say x of t or x of omega. You can obtain the frequency domain representation by taking the Fourier transform of this. So if we take Fourier transform of x of t or x of omega, we obtain x of omega. Means if x of t or x of n is given, we can obtain the frequency domain representation by taking the Fourier transform. Or if x of omega is given, and if we want to have the time domain representation, we can take the inverse Fourier transform of this, and we'll have the time domain representation. So domain simply means either the time domain representation or frequency domain representation. All right. But whether I say time domain or frequency domain, it means one and the same thing. Means I'm talking about the same signal. I'm talking about the same signal or same information that signal is represented. All right. So this is the notation that will be followed. Now, two important operations that you must remember before we proceed with the sampling and reconstruction operation. So two important operations that you must remember before we proceed this sampling. Now first is if we convolve any signal with delta signal, means if we take the convolution of x of t with delta t, or if we take the convolution of x of n with delta n, or even x of omega with delta omega, the output of these operations is simply the signal itself. Means it will be, if we take this convolution of x of t with delta t, the output will be x of t. Same way, if we take the convolution between x of n and delta n, the output will be x of n. And same way, if we say x of omega is convoluted with delta omega, the output will be x of omega. So this is the output of this operation. So if you convolve any sequence or signal with a delta signal, the output is the signal itself. Now one implication of this means another implication of this is if we have the shifted version of this delta, means if I say now x of t is convoluted with shifted version of this sequence. Well, and same way for x of n and delta n, means if these are also shifted, or in frequency domain these are shifted. So if you convolve this signal with this, one implication of this is simply replace this. The output will be the signal itself, means the output will be x of t. But what will happen to the argument? Replace t by this argument. Simply replace t by t minus t. So this same is true for this x of n. Means it will be simply x of n minus n. Same way, if it was a frequency domain representation, means this is the convolution between these. The convolution operation will be equal to x of omega minus omega. So this convolution operation gives you the signal itself, whether shifted version or this not shifted version, that's one and the same thing. So convolution of any signal or sequence with delta is the signal itself. And the second operation that you must remember is two signals or sequences are multiplied in one domain, they will be convolved in the other domain. Means the signals will be, if two signals are convolved in one domain, in other domain these will be multiplied, and vice versa. So if two signals are multiplied in one domain, in other domain these will be convolved. You must remember this thing. What is the meaning of this? In other words, if I say x1t is multiplied with x2t in time domain, then in frequency domain these will be convolved, means we'll have, sorry, let me represent the frequency domains by capital letters. So in frequency domain these will be convolved. So this is the meaning. Same way, if two sequences, if these sequences are multiplied in frequency domain, then in frequency domain, in time domain, these will be convolved. These will be simply x1t convolution with x2t. Same is true for discrete time. Same is true for exactly discrete time. In other words, if I say x of n is multiplied with x2 of n, then in this domain, the spectrum of these two will be convolved. So this x1 omega is the frequency domain representation of x1n, x2n is the frequency domain representation of this. So you must remember, if two sequences or signals are multiplied in one domain, in other domain these will be convolved. These will be convolved, and this is actually the beauty of transform. It converts the convolution operation to a multiplication operation. See, this is the beauty of transform theory. If the two sequences are multiplied in time domain, these are, sorry, this will be convolution operation in frequency domain. So it converts the convolution operation to a multiplication operation. Check it. All right, so this is actually the important advantage of transform theory that we actually exploit in signal processing, that we shall learn later in the course. So two important signal operation that you should remember first. If you convolve any signal with delta, the output is the signal itself. Second, if you multiply two sequences or two signals in one domain, in other domain, the signals will be convolved, whether in time or in frequency domain, and vice versa. So you must remember these two operations to see the result of this sampling operation, or to learn this sampling operation and reconstruction operation. So in these few lectures, we learn how to first convert a continuous time signal to a discrete time signal. Then how do we reconstruct back the continuous time signal to the to this discrete time signal to the continuous time signal. And in the second part, we will learn one important condition: the rate at which you should sample the continuous time signal to recover back probably from this discrete time sequence. All right, so this is what we are going to do in the next few lectures. Let me stop here. In the next session, we'll start with the sampling operation. All right.